In this chapter, we'll talk about what heads in and heads out refers to, why it matters, rim brake and disc brake wheels, pulling and pushing spokes, and I'll give you my recommendations and rationale. On the topic heads in or heads out, there are plenty of theories about. You'll be on the right path if you follow the math. On that point, I have no doubt. Details sometimes make a difference with bicycle wheels, and one really nerdy topic is the concept of lacing the spokes, certain ones, heads in or heads out. You may not have any idea what I'm talking about, but just watch this chapter and you'll come to a basic understanding of what heads in and heads out means. For a recommended heads in or heads out orientation, we'll look first at the recommended lacing for a bike with rim brake, and then the recommended lacing for a bike with disc brakes. You'll see some nice graphics. This is a flange on a hub. We see the free hub body, so we know we're looking at it from the drive side. A representation of a cassette. And then we can quickly remove the cassette. Here we see a wheel. As we pedal, a torque is applied to the hub, and the torque is transferred to the rim by the spokes, and the wheel turns. The spokes shown here are called pulling spokes because we imagine that they pull the rim around as the hub turns. There are two ways I can lace up those pulling spokes. One is, as shown here, with the pulling spokes heads in, and the other is with the pulling spokes heads out. Which is better, pulling spokes heads in or pulling spokes heads out? Well, it depends on the type of bicycle. Does the bicycle have rim brakes or disc brakes? So the question becomes, which lacing pattern, heads in or heads out, allows the wheel to best handle torque? I'm going to give you a rationale on why I think it's better for a rim brake wheel to have the pulling spokes heads in, whereas for a disc brake wheel, I think it's better to have the pulling spokes heads out. This is my recommended lacing for a bike with rim brakes. We have the heads in pulling spokes. There's the free hub body. So when the free hub body turns, the torque is transferred to the rim by these pulling spokes. Here's the completed wheel with the pulling spoke heads in and the pushing spoke heads out. Here are the pulling spokes heads in and the pushing spokes heads out. In a stationary wheel, the pulling spoke tension is equal to the pushing spoke tension. For a rim brake wheel, the highest torque load occurs when accelerating. When you accelerate, the pulling spoke tension increases, and the tension on the pushing spokes decreases. But no matter how I lace up the wheels, the pulling spokes, whether they are heads in or heads out, the tension on those is going to increase when I accelerate. So why does it make a difference how they're oriented? And to answer that question, we need to look at some diagrams. I'm going to build another wheel starting with my venerable Shimano 105 hub. Those are the ends of the lock nuts. The overlock nut distance is 130 millimeters. If that's the center of the hub, I have 65 millimeters from each lock nut to the center. With a caliper, I get 28.4 millimeters left lock nut to left flange. On the other side, 44.8 millimeters right lock nut to right flange. Flange thickness on the left side of 3.0 millimeters, 3.9 on the right side. On the left side of the wheel from 65 millimeters, I'm going to subtract 28.4 and subtract 3.0, and that will give me the center to left flange distance of 33.6 millimeters. On the right side, we similarly subtract from 65 millimeters 44.8 millimeters and 3.9 millimeters, and I get a distance from the center to the right flange of 16.3 millimeters. And that gives me these dimensions from the center of the hub to the outside of the flanges of 20.2 millimeters on the right side and 36.6 millimeters on the left side. If I build my wheel up with the pulling spokes heads in, then I get in these two legs here of the two right triangles that form 36.6 millimeters on the left and 20.2 millimeters on the right. Now, even though it appears in the graphic as if these spokes here are radially laced, they're really tangentially laced. So that graphic there is equivalent to this picture that we see here. For the wheel I'm building, I have used an online calculator and come up with 291.96 millimeters length spoke on the drive side, 293.52 millimeters on the non-drive side. A little trigonometry gives me 3.97 degrees here and 7.18 degrees here. And here's a second hub, another rim, the center. In this case, we're going to lace this up, though, so we have the heads out on these spokes. There's the line that creates two triangles, and these are now the dimensions of those short legs of the triangle. Those distances are a little bit shorter. My spoke length calculations come out exactly the same, but because those opposite sides are shorter, my angles are different. I get 3.2 degrees on the drive side and 6.55 degrees on the non-drive side. Let's take this diagram and put some tension on these spokes and see what happens. So we're going to represent 120 kilograms of force on the drive side spokes of that wheel on the left, and that is represented by the length of that vector. Now that vector can be resolved into a vertical and a horizontal component. And when I calculate the force on that horizontal component, I get 8.30 kilograms of force. On the non-drive side, I find that I have 66.4 kilograms of force represented by vector, and that also can be resolved into a vertical and a horizontal component, and the force part of the horizontal component is also 8.3 kilograms of force. Now with the other wheel, I find I have different values because of the different angles. Once again, we'll use 120 kilograms of force on the drive side, represented by that vector, which resolves into a vertical and a horizontal component. But my force magnitude on that horizontal component is only 7.0 kilograms of force. And on the other side, my 61.4 kilograms of force on my vector for my non-drive side spokes also resolves into a vertical and a horizontal component. And once again, I find I have 7 kilograms of force on the non-drive side. I think it comes down to this. When you're accelerating, the tension on the pulling spokes is going to increase, and therefore the tension on the lateral component of that tension vector is going to increase also. I think you're best off if the lateral tension starts at a higher level to begin with, so that the wheel on the left at 8.3 kilograms of force with the heads in orientation, I believe, is better.
Now, from a structural standpoint, let's take a look at a key difference between wheels that have rim brakes and wheels that have disc brakes.
Here we're looking at two disc brake wheels with the rider going in the direction shown there, and we're looking at this from the drive side, and the wheels are turning, and we want to take a close look at how we've laced up these hubs. These are two disc brake wheels viewed from the right or drive side. In the case of these disc wheels, we've laced up the wheels differently because you can see that the pulling spokes in blue are heads out and the pushing spokes in green are heads in, just the opposite of how we laced up the rim brake wheel. Here we're looking at the wheels from the non-drive side, so the rider is now going to the left, and here we see the wheels turning in the direction shown. So my rider is rolling along in the direction shown. And now the rider has to suddenly stop. So let's take a close look at the lacing in the hub and see why the different lacing pattern is an advantage in this situation. Here's a close-up of the hubs, and these are the bolt holes to which the brake rotors would attach. When I stop the bike with my powerful disc brakes, I'm really stopping the hub, but the wheels want to keep turning because of the momentum of the bike. In this case, the purple spokes become the pulling spokes because the hub tries to pull the rim backwards to try to stop it from turning, and the pulling spokes here are laced heads in. The blue spokes are the pushing spokes, and they're laced heads out. So I've built up these wheels with the opposite heads in, heads out orientation as I did for the rim brake wheel. We lace it up this way because in most instances, the torque on the wheel when you stop the disc brake wheel is much larger than the torque placed on the wheel when you accelerate. That fact will be explored deeply later on in the chapter about acceleration and deceleration. If all these things we covered in this chapter are not crystal clear in your mind, don't worry, because we're going to come back to revisit all these topics.